Dear friends, welcome to this program called KAAPI with Curiosity, which we have initiated a few years ago, and it has been attracting a lot of people, great science enthusiasts of different age groups. As you know, this is a joint program of the Planetarium and ICTS. And as you know, the Planetarium is engaged in various kinds of activities for different age groups. So we have small children coming here as well as very elderly people but still interested in science. And this funny arrangement of this auditorium is, as you can guess, is below the Sky Theatre. And even with this kind of a small arrangement, people have been coming here very regularly and enjoying all these lectures. And it is now time for us to request some of you to come and join us as volunteers, because we have so many activities, as you could see outside. Apart from the Sky Theatre shows and these kinds of educational activities, we have a lot more things happening in small rooms inside this building at other places. So I take this opportunity to tell you that if you are interested in helping the planetarium conduct its activities and make it reachable to a larger audience, we would like to have some of you as volunteers. So if you are interested, please send us an email. The other details are given there, and you can go through what are all the different kinds of programs that we have and how we will be able to help you. In fact, if you see the Sky Theatre show now, you will see that there is plenty of scope for you to help us in those productions also. We have been making our own programs all these years, and we will continue to make hereafter also. So please join us, and then now I request him to, Amitabh, to tell about ICTS and introduce the speaker, who is going to give a wonderful talk on the symmetry and laws of nature.
Okay. So again, on behalf of ICTS, I would like to welcome all of you for this KAAPI talk. Many faces are already familiar to me, so I know you have been coming here regularly. Just a couple of words about ICTS. It's a center for the Tata Institute of Fundamental Research, located in Shivakote, quite far from here. But so ICTS conducts, of course, in-house research activities, but in addition, there are outreach activities of various types. We are, in fact, starting new outreach activities as well. One is a set of activities called Math Circles. Sudarshan is there, you can talk to him afterwards. So these are related to basically having young children get interested in mathematics in general. Mathematics as a subject, not mathematics as an exam topic. And we have also outreach activities really that will be coming up soon. Science Hub, hopefully within a few months. And the third main activity of our ICTS is the programs, and there are programs on all sciences. You also interface between experimental and theoretical sciences and so on, and all that information is on the webpage, so I will not really spend too much time talking about the program activities. So coming to today's talk, it's a pleasure to introduce Professor Umesh Waghmare from Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. And so he did his bachelor's BTech in engineering physics from IIT Bombay. Afterwards, he went to Yale for a PhD, also in applied physics. And after postdocs in Harvard, he joined JNC in 2000, where he has been since then. His main research interests are in material science, but ab initio calculation, which means that you try to calculate the properties of materials starting from fundamental principles of physics. And that is his main activity, essentially closely related to what he will talk about, the laws of nature, and how we can actually use them to calculate properties that you can then experimentally verify in labs, and sometimes even the kind of properties that you cannot verify experimentally because experiments are too difficult to be done. in those situations. So without further ado, I will ask Professor Waghmare to give his talk. But before we start, I would request Dr. Shaileja to give him.
Thanks, Amit. It's my pleasure to be here. And I'm grateful to the Planetarium and also ICTS for this forum of KWK, through which I have this opportunity to interact with large number of students and public in general area of science. And I'm going to share with you some really very deep principle in physics, basically called symmetry principles. These also apply to chemistry and to some extent in biology as well. Okay, but by and large, what I will be telling you about is physical laws of nature, and you will see that actually nature and its laws are two sides of the same coin, which is made up of symmetries. Okay, so symmetry is really very fundamental to the way we think about nature and at least the physical description of nature. I come from Jawaharlal Nehru Center, which is funded by the Department of Science and Technology, Government of India. We have master's and PhD programs in material sciences and biology in this center. Okay. So symmetry. All of us have some notion of symmetry, I'm sure, because from the childhood, even while our eyes learn how to see, that time itself the notion of symmetry gets ingrained in the way we think about the surroundings around us. So here is a butterfly, and it's without any thought, you can immediately tell, oh, how beautiful it is, and probably it's linked with its reflection symmetry. It has a line here which divides it into two very equal looking parts. Here is a sunflower, which is also very interesting design. It involves some golden ratios from mathematics to generate this spiral symmetrical pattern at the center of the sunflower. So nature, of course, has symmetry evident in many aspects of it. Long ago, this was 370 BC, the philosopher Plato thought about certain objects which were really very interesting objects. These are the only convex polyhedral objects around, and these are called as Platonic solids, named after Plato. And you can see each of them, tetrahedron, octahedron, cube, actually these three are linked with each other. You will see as we go through this lecture, and you will see the evidence for this as well in nature, icosahedron and dodecahedral type of things. But there is a fundamental difference between the two you will see when you start making extended crystals out of them. Okay. This was 370 BC, and that's when these highly symmetric objects appealed to the philosopher Plato. Okay, and only half a century later, Euclid actually showed some certain mathematical properties of these Platonic objects. Symmetry also is very integral part of how we think about beautiful art and geometric forms which are created by humans, whether they come from the Eastern world or they come from the Western world. You know, symmetry is always there in the artistic forms that we have. In fact, if you examine the artistic forms, they always involve mixture of symmetric things and asymmetric things. And we will get some flavor of this not symmetric or asymmetric things also in this talk. So the bottom line is the notion of symmetry is ingrained in our perception of nature and beauty. In fact, some people often wonder why symmetry is so essential to many aesthetically appealing objects in nature or beauty, the notion of beauty that we have. So by the way, the presentation is planned such that even the high school students should be able to follow it. So if some of you are experts and experienced, I apologize, but I'm sure you will find certain things in this presentation which will be good things to take home with you. So symmetry, the first definition of symmetry was given by mathematician Weil. He said, do something to an object, and if the object is unchanged, something that you did is the symmetry of that object. Okay, that's the starting definition of symmetry, and that links you to certain mathematical terms. One is called transformation. Transformation is essentially linked with what you do something to that object. You rotate it or reflect it. The second mathematical term is invariant, means that object remains unchanged. You will keep seeing this term again and again in this talk, so please see it now. And symmetry property basically is linked with the fact that whether the object is invariant or not invariant. Let's take this simple example. The picture is shown here, made up of 4 semicircles. And if I rotate it by 90 degrees, for example, this particular wing will come horizontally over here. But the object is exactly the same as what I started with. Okay? And the answer is yes. This object is unchanged, it's invariant under this 90-degree rotation, and hence this such 90-degree rotation is a symmetry property of this object. Okay? Second question I ask is, I work with the same object and I put a vertical mirror. You can put that mirror at the center line of this object as well, and mirror reflect this object and ask whether it's the same. And you will find out actually no, it's not quite the same. Right? It's mirror reflected and it's different. So mirror reflection in y plane is not a symmetry property of this object. Okay? So this is a simple illustration of how I can go about determining symmetries of an object. Is it clear? Please feel free to stop me anytime if something is unclear. Very good. Let me go to the next one. There are many types of symmetries. And the first one I show here is to demonstrate what is called as rotational symmetry. So if I rotate this object by 60 degrees and multiple of 60 degrees, I get the same object back. You see, on x-axis I'm showing you the angle with which you can rotate this object, and you have basically 6 angles which will define the rotational symmetry of this object. And that's why this is called as discrete symmetry. Means there are specific values of angles for the rotation of which that object is invariant. On the right hand side, I have a circle. And if I rotate that circle around the z-axis which passes through the center of the circle, you will see it's invariant. Whatever angle I choose to rotate the circle, it remains the same. Right? So this defines for us what is called as continuous rotational symmetry. That means the angle that under which I can perform a rotation is a continuous variable x from 0 to 360 degrees. Is that clear? Yeah, very good. So you now understand what is discrete symmetry and what is continuous symmetry. The next example is what is called as spatial translational symmetry. Means I have an object here, I translate it in real space and ask whether the object is unchanged. Okay? Here is a picture of an array of small little objects. You can also think of them as tiling, and for this purpose you imagine that it's extending from -infinity to infinity. What you will notice is you can translate this object from any one point to the next object nearby or the further one, and that under those translations this array is invariant, it's unchanged. Okay, so this is spatial translational symmetry. It's an infinite set of symmetry operations, but still they are countably infinite operations. I can label each operation by an integer. Translation along x-axis by 1, by 2, by 3 units of length that I can say. On the other hand, on the right hand side, I have an infinite box of jelly. Okay, every point in that box looks the same. I look here, I look there, I translate around, it's the same. So that is called as continuous translational symmetry. I can displace from any point to any other point within that object and nothing changes. Okay, so this defines continuous translational symmetry. So there is also a similar translational symmetry in time, and that's called temporal translational symmetry. And why am I now talking about temporal symmetry, right? Suppose I do an experiment today and find an outcome about certain scientific observable, and tomorrow you repeat it, you should find the same thing. If it doesn't, it's not the same, there will be no way we can do science, right? So this symmetry is also very important, and we will see later in this lecture what are the consequences of that symmetry are. So this is a slightly crowded slide. I will go slowly through it, but it's a very important slide. You know, it will be useful to the students here in the audience in doing certain homeworks in their class, or maybe at the college level even. So various symmetries involving electric and magnetic dipoles, or charges for that matter. Okay, and the symmetry that I'm going to define you to begin with is reflection symmetry. You already know what reflection symmetry is. If I have an object T and I reflect it along this center line, it remains the same. Yeah, that's reflection symmetry. We know it well now. Now I want to apply that symmetry to certain things which you know from day-to-day life, right? Electric dipole moment. For example, an electric dipole moment is defined as a vector or a line, directed line, from a negative charge to a positive charge. And I'm going to label it as P. P is the electric dipole moment. And I mirror reflect it in this vertical plane. What do I get? Well, this negative charge is closer to the mirror, it will be here. Positive charge gets reflected here. And what happens to the electric dipole moment? It's reversed, right? So P goes to minus P under reflection symmetry. Remember? Now I have a magnetic moment below that. A magnetic moment is not so simple to think about, because of course you know it involves north and south pole, but there is no north and south magnetic monopole. So the way I will introduce to you about its symmetry is by saying that a magnet, bar magnet, is produced when you have a loop of electrical current, or a positive charge which is looping around in a circle. It creates a magnetic dipole moment which is perpendicular to it along the axis given by this direction using some right hand rule, right? Something you studied in the high school days. Now I reflect this in the mirror plane. What do I get? Well, you see it's moving this way. If in the reflected side also, it will be moving the same way. Same way, you can look at the arrow, velocity of the charge. So what you see is, if you mirror reflect, the magnetic dipole moment is unchanged under mirror reflection symmetry. Clear? Yeah. Good. So you learn two fairly non-trivial things, right? What I prove here for electric dipole moment also applies to the corresponding fields. Electric field is also or under the parity transformation, or reflection transformation, or magnetic moment is even under this transformation, symmetry operation. The next operation symmetry I want to introduce is spatial inversion. Spatial inversion basically takes a position in real space R to minus R, right? It's a little different from parity. They both often are called as parity, but mathematicians like to differentiate them because in different dimensions they can mean different things. So for example, this is a cube I have, and I have the inversion center of the cube is at the center of the cube. And if I apply inversion symmetry, this green corner will come to this green corner, yellow corner will go to this yellow corner, and this will go to here. That defines inversion symmetry. Is that clear? Very good. So what happens to the dipole moments if you apply inversion symmetry? You can also show that P goes to minus P and mu goes to same. It remains unchanged. Okay, and here I'm showing you an example. If I have an object like this, it's even under inversion. But if I have a cube where one side is positively charged and the other side is negatively charged, it breaks the inversion symmetry. Okay, so moment you have electric dipole moments, you don't have inversion symmetry. You break inversion symmetry, or you break reflection symmetry. The next one is even more interesting. It's called as time reversal symmetry, and it's not something we imagine in day-to-day life, but it's very fascinating. Someone will say, well, can we go back in time? That symmetry is linked with that. Well, even if many things don't go back in time, for example, if I break a glass, I can't go back in time and reassemble it. You know it well, right? But certain physical laws allow you to go back in time, and in the following way. So t goes to minus t, and again electric dipole moment, since it's a stationary object, it is unchanged under time reversal symmetry. P remains the same as P if you apply time reversal symmetry. But now behold what happens to the magnetic dipole moment. That's interesting, right? So magnetic dipole moment involves moving charges. So when you apply time reversal symmetry, the velocity of these moving charges will reverse, so this will become oppositely oriented like this, and you will get a dipole moment which is opposite of this. So if you apply time reversal symmetry, electric dipole moment remains unchanged and magnetic dipole moment changes its sign. Okay. In fact, this is already going to be enough for you to explain why you cannot use electric field to change magnetic dipole moment, because the symmetries are not going to allow that. We'll look at it more carefully later. The last bit of introduction in the context of symmetry is chirality. It's a very important concept, particularly if some of you are interested in biology and also chemistry. Of course, it's very important in physics as well. So chirality is kind of an asymmetry. Okay, it says, for example, look, if you look at this object, it has a purely rotational symmetry, but it lacks any reflection symmetry. Right? This is also another object which is it has a threefold rotational symmetry, but it lacks any reflection symmetry. And moment you lack any reflection symmetry, what you get is called as handedness. Your left hand and right hand. And for example, I'm showing you here a molecule, a chemical molecule called amino acid, a specific kind of amino acid. And you will see if I mirror reflect it, you get a copy which you cannot superimpose on the same molecule. Okay? And such molecules are called as chiral molecules. In fact, as a result, most biological organisms are polarized in this sense, one way or the other. When you say I'm right-handed, your right hand is more skillful than the left hand. Even in the shells which are formed, most of the shells that you will find in nature, which are built by certain species of snails, will be right-handed. In fact, you will find some books with the title "A Lucky Seashell." The seashell, if you find the seashell with a left-handed structure, which is very rare, you are lucky to find it. Yeah. So these are the effect of symmetries, very vivid effect of symmetries, how it in the macroscopic world, it is influenced by something which occurs at a molecular level. These amino acids are involved in interactions with the DNA molecules, RNA molecules, and proteins that are formed from these amino acids. And those are also of the same handedness. And as a result, you get these macroscopic features which also obey handedness. So this is a very important concept, remember that. Okay, so now we have a little break for questions. If some of you is curious, and particularly students in the audience, can you tell me what is the symmetry of this object? Something you see? Rotation? Which rotation? 90 degree only? And 180 only? 360? And? Yeah, 3 times that, right? So see, this is the key thing. Once you apply a symmetry operation, you can keep applying it again and again. The object will not change. And that way of building up the symmetries forms a set of symmetries which is called as the symmetry group of that system. What about the cube? This is a much harder question. How many symmetries does a cube have? Sorry?
It has mirror and rotational symmetries for sure.
Which rotation?
Multiples of 90.
Sure. Sorry? Yeah. Okay. See, this is why, if you start thinking about things in a sort of this very systematic way, things become very enjoyable, and they also will help you in your other works. So one axis of rotation you may not have realized the cube has, it has a 126-degree rotational symmetry. If you go in the axis which goes from this corner to this opposite diagonal corner, diagonal of the cube, if you see, it has a threefold rotational symmetry, 120 and 240 degrees. So there are a lot more symmetry operations. But the question is, if you have to list them, of course, it's an enjoyable experience. I give it to you as a homework, at least for the students here. But I'll tell you how to count these symmetry operations very quickly. Yeah. So if I put an x, y, z axis at the center of the cube, x, y, z. Any operation I do such that these orthogonal three axes are preserved is a symmetry operation of the cube. So x-axis can go to minus x-axis, it can go to y-axis or minus y, it can go to z or minus z. So there are 6 possibilities that x-axis can transform to. Once I transform x-axis, I have y-axis left. It can transform to 4 remaining directions. And then this goes to only remaining 2, plus and minus. So 6 times 4 times 2, that gives you 48 symmetry operations of a cube. Okay? So this is one way you can immediately enumerate the symmetry operations of the cube, and then that will make it easy for you to see how to classify them in different classes and so on. Okay, good. So we have enough background in thinking about symmetries. Of course, so far we have thought about symmetries of objects, but the take-home message on this talk is actually objects are no different from the physical laws that apply to them. So symmetry of physical laws is going to be equally interesting as well. Okay, so good. The first interesting thing I want to tell you, why are we caring about symmetries, is a very powerful theorem by Amy Noether about 100 years ago. She was a mathematician who proved a beautiful theorem, absolutely most appealing theorem, which Einstein called her a genius for. Okay, so the theorem is about conservation laws. All of you know conservation laws, right? You use them in your work. In fact, you usually use them to simplify the solution to a problem, physics problem. So here is a problem which is little difficult to do otherwise. A ball is rolling down this roller coaster, and it makes a revolution and goes forward again. The question is, what is the minimum height from which that ball should be dropped so that it can do this motion? It's a question, if you try to use Newton's laws of motion or otherwise, is not so simple to solve. But if you use conservation laws, in 4 steps you can get the answer, and the answer is given there. Okay? You can work it out. Basically, the ball comes from here to here, energy is conserved, you know the velocity, and once it enters a circular loop, you know the relationship between acceleration and velocity, v square by r, and then basically it allows you to solve the problem. Okay? The conservation of linear momentum is shown here. If this ball pendulum and set of pendulums, if it hits here, the momentum is transferred from one to another, and the other one goes to the opposite side. And that's a demonstration of conservation of linear momentum. The one below is conservation of angular momentum, something you can try it out in merry-go-round in the parks. If you are rotating with your hands wide, or you are on the periphery of the merry-go-round, and then you go to the center of it, your moment of inertia becomes less, and you suddenly start revolving at a much higher angular velocity. So the product of angular velocity and moment of inertia is conserved, and that's conservation of angular momentum. And the natural question is, well, these are very useful things to have. They allow you to solve many problems, understand many things you see around you, but what is their origin? Where do they come from? And that's where Amy Noether showed that symmetry basically gives you a conservation law. So first of all, let me define what symmetry she talked about is. Just like I talked about symmetry of an object, she says symmetry is a transformation upon which the total energy of the system remains unchanged. This is easier definition if you are thinking about day-to-day objects and their motion. Because nothing is translationally invariant, because if I say I keep going to the left, I will hit the wall. And you will say, of course, this is not translationally invariant. But this definition helps you in thinking about it. So if an object is moving in free space, it's a translation in free space is a symmetry operation. Its energy doesn't change. But if that object is near a heavy planet, the gravitational potential energy of that object changes as it comes closer to the planet, and as a result, it doesn't have the translational symmetry in the space. So this doesn't have translational symmetry. What about this object, something which is rotating around the Earth? It does have a rotational symmetry, if I ignore things far away from it. Right? So this is a rotational symmetry because the energy of this object depends only on the distance between this object and the center of the Earth. And if along a circle it doesn't change, its energy is unchanged. Right? So this has a rotational symmetry. Similar symmetry is in translation in time, an object moving in time, and if its energy doesn't change, it is invariant under translation in time. So the Noether's theorem says, for every continuous symmetry, you have a conservation law. For example, if you have translation in space, which is what I showed you here, you have conservation of linear momentum. If you have rotational symmetry, continuous rotational symmetry, then the angular momentum is conserved. And if you have translational symmetry in time, your energy is conserved. Of course, this is a bit repetitive, but it has certain meaning in quantum mechanics. So that's why I'm keeping it in this list. Yeah. So very systematic analysis. The proof of it is not difficult. But since I assumed only the high school background, I didn't go into giving a proof of this theorem. But it's not difficult to imagine. It basically involves Lagrangian principle, which is a minimization principle. And if you go from one trajectory of an object to a parallel trajectory object, and the Lagrangian action doesn't change, well, you have a conservation law there. Yeah. So the quantity which is conserved is called as a generator of the transformation which that symmetry corresponds to. Again, not intuitively very appealing, because you can see linear momentum is what translates you in space. If your momentum is 0, you don't move in space. Angular momentum, if you have 0 angular momentum, you will be sitting in one place. If it's non-zero, you are going to rotate around certain object. Yeah. So that's the beauty of this theorem. Generator gives you transformation of that symmetry. And in fact, it's even more powerful. It does not only, it says given a symmetry you have a conservation law. It says if you have a conservation law, there better be a symmetry. So many times, if you do experiments in this very high energy accelerator type setups and you find out certain thing is conserved, you go back to your theory and ask, do I have some additional symmetry in my theory? There has to be. And that's how you discover new symmetries and aspects of the system that you have. Okay? So one of the most powerful theorems which border mathematics and physics and has influenced physics in the last century. Second example is conservation of parity, something maybe many of you are familiar with. I will just take a minute to tell kids here that electrons in an atom basically occur in quantized energy states which are labeled by orbitals, s orbital, px orbital, py orbital, and pz orbital. Okay? And if you want to excite an electron in an atom by light, by absorption of light, right? So you have light which is coming in and you excite that electron to the next orbital available to that atom. What is known using Laporte's rule is electron cannot be excited by light from s orbital to another s orbital. It can only be excited from s orbital to p orbital. And this also involves very similar idea that we learned so far, conservation of parity. Because parity of s orbital, you see, is spherically symmetric, is even. Parity of p orbital is odd, because if you apply reflection symmetry, it goes to minus of itself. So it is odd in parity. That's what is written here. So if you want to go from even state to odd state and the light is having odd parity, electric field is odd under parity, something we learned on the second slide of this lecture. That law is proven basically by the conservation of parity. Yeah? So symmetries tell you what processes are possible in nature. Now, this is probably the most sort of deepest aspect of symmetry in physics, symmetry of physical law. Earlier we talked about symmetry of object. Now we talk about physical laws which apply to those objects. So physical law by definition is a relationship between physical quantities, which is typically given by equations, but I am told I shouldn't use equations in this talk. So basically this is the simplest equation I'm sure everybody knows, Newton's law, F equals ma. So these equations or relationships should not change upon symmetry transformations which are basically governing that system, right? Let's take example of gravity. Gravity, you all know that the gravitational force between two objects is essentially inversely proportional to d squared, right? D is just the distance between the two objects. Now, if I measure the force sitting in this frame of reference or rotated frame, translated frame of reference or rotated and translated frame of reference, it will not change my result. Why? Because the distance between the two objects is unchanged. It's invariant if I go from one frame to another. So, by construction, gravitational law does not change under rotations or translation in real space. Clear? Good. So, translation in time, same thing. If I measured the same force tomorrow, it will be the same, provided the distance between those objects is the same. Right? So these are symmetries which govern physical laws, and then they require that physical law should not change under those symmetry operations. So Einstein made a very, very remarkable took a very big step here. Okay? He said invariance of laws in all inertial frames. Inertial frames means if I'm doing a measurement here on this table and another person is doing same measurement sitting in the bus on the road on a similar table, everything is the same, our measurement should match. The physical laws that we determine from these experiments should be the same. That's called relativity, right? That frame is moving relative to me. But in fact, if you look at physical law, you cannot tell whether I'm moving at all. That was the spirit of Einstein's theory. And of course, the constancy of speed of light, which was linked with the electrodynamical equations called Maxwell's equations. So what Einstein basically proposed is, and which was also related to work by mathematician Poincaré, is that there are symmetry operations which involve translations in space, translation in time, rotations in real space, and what is called as Lorentz boost, meaning the transformation which relates measurements in stationary frame to a moving frame. Those are called as Lorentz boost. And if you combine all these symmetry operations together, you get a big symmetry set or group called Poincaré group. Okay? And the idea is the laws of nature should be invariant under these symmetry operations in Poincaré group. In fact, much of the standard model that you are aware of, gluons, quarks, neutrons, essentially is linked with this principle. Right? And Wigner, he is the mathematical physicist who got a Nobel Prize in '63 for the work on symmetries, mathematical aspects of symmetry and applications to physics. He showed that the elementary particles that you come across in the standard model are actually related to the irreducible representation of Poincaré group, meaning how those fields of particles transform according to the symmetries in Poincaré group determine which particle you have. Okay? So this was sort of the fundamental aspect of how symmetries constrain physical laws, how they determine physical laws, what form of physical law can be possible. Implications of symmetry. And here is, once you know physical law, for example, you know Schrodinger equation, or you know Newton's laws of motion. You will use Newton's laws of motion to study motion of Earth around the sun. Or you will use Schrodinger equation to find out electronic state of p orbital, for example. Right? And what it says is, if I apply rotation, see, this is the power of symmetries now. If I apply a 90-degree rotation, I will get another orbit of Earth around the sun. And that is a very valid, mathematically correct orbit of the Earth around the sun. right? So knowing one solution of equation of state, I can immediately come with next new solution of equation of states, which is related by symmetries. It becomes even more interesting in quantum mechanics. If I start from px orbital, and if I rotate it by 90 degree, I get py orbital. And by construction, I know that this has to be same as this in terms of its symmetry. So if this is a electronic state of my atom, this is equally valid in an electronic state of my atom. Not only that, it has to have the same energy as this state. You know, that's the power of symmetries, that knowing one solution, you can determine new solutions. And of course, in quantum mechanics, what is called as degeneracies of states or orbitals is essentially linked with these ideas. Okay. So states can be classified and labeled based on how they transform under symmetry. For example, the quantum numbers that you see on electronic orbitals, NLM quantum numbers, principal angular momentum quantum numbers, they are all linked with how they transform under symmetry. The mathematical name for that is called irreducible representation of the symmetry group. Okay. So let me come back to some very day-to-day question. Can electric field exert a force on a magnet? This is sort of an exercise to tell you how you can use these symmetry principles to solve some very interesting problem which otherwise are not so easy to solve. The question is imaginary, right? Can I use electric field, apply it to this bar magnet, S bar magnet, and can it change it? Can I move it? Or can I change its magnetic moment? That's the question. Now to do that, I will do what is called a symmetry analysis. Again, very simple symmetry analysis. There are two symmetries I will consider. One is called parity, which I introduced earlier, and one is time reversal. And you all know from that analysis that magnetic dipole moment is even under parity and odd under electric dipole is odd under the parity, and vice versa under time reversal. So if I apply parity operation to, this is my system, electric field applied to bar magnet, and I apply parity inversion symmetry or reflection symmetry. What do I get? Well, the bar magnet remains the same because it's even, and electric field is reversed. So what it will mean is, if I apply symmetry of my system, I get a force which should be opposite of what this force should be. Force is equal to minus of force. Similarly, if I apply time reversal symmetry, the bar magnet gets reversed, N comes to the left hand side, and electric field is unchanged. So as a result, the action of this applied electric field on the bar magnet again should be minus. So this force is equal to minus of this force, and that cannot be the same, I mean, correct, right? Then they have to be zero, right? So that's the proof, which is based on just simple symmetry principles. Why you can't use static electric field to change the magnetic dipole or bar magnet, you know? How will you otherwise prove it? Yeah? Of course, you can use Maxwell's equation and show that, well, unless I have time-dependent fields, I can't get a force, right? That's possible, but this is a very simple proof. Not only that, it has a huge, powerful content in it. Suppose I want to think, this is constrained by symmetry, but I am imaginative. I want to think of a material where, you know, I can change its magnetic moment by applying electric field. Why not? We have to be imaginative. How would you do it? And the answer is here. Well, I will have to think of a material which will break time reversal as well as inversion symmetry, parity symmetry. If I can think of an object which breaks both of these symmetries, bingo, you have that system where you can apply electric field to change its magnetic field. In fact, we will see something like this by the end of this lecture today. So another very important, probably one of the most important aspects of symmetries is the principle of spontaneous symmetry breaking. Okay, and I'll first give you a physical example where this happens in, again, very day-to-day accessible. This also happens in cosmological scale or in high energy physics, but I'm going to give you an example where it's really in the tabletop experiment. So if you take a magnet, it has a magnetic moment which is aligned in some direction. That magnetic moment is arising actually from the fact that little magnetic moments of different atoms which are randomly oriented, but in average sense they have some non-zero moment in a given direction. As you heat it up, they all become random, and average magnetic moment as a result is 0. Okay, that's called paramagnet. That's called Curie temperature, Tc. So this high symmetry phase, this phase has all symmetries. Although locally you see that magnetic moments of each atom are random, in average sense it has a huge symmetry. It has a rotational symmetry. And that corresponds to this high energy state in the Mexican hat-like figure. This is energy along z-axis, and x and y-axis could be magnetic moment along x and y-axis, for example. Okay? So at high temperature, the entropy is high and it stabilizes this unstable point. But as you cool it down, it goes to this low energy state, which is basically polarized, magnetized in a specific direction, and that's a low symmetry state, low temperature state. And this order parameter, this is called as symmetry breaking order parameter. In this case, it's magnetization, okay, along x or y direction. That breaks rotational symmetry in magnets. Okay, this is the simplest example I can give you of what is known as spontaneous symmetry breaking. As you cool down a magnet at Curie temperature, it breaks rotational continuous symmetry. Very good. Now we'll come to even more simple things and find out how fascinating the implications are. Okay, so I start with a solid material, and in this solid I assume that it's crystal. Okay, I have a crystal and I heat it up along this axis by increasing its temperature. You all know that solid will become liquid, liquid will become gas. And based on that, in one of the earlier KAAPI with Curiosity lectures, Deepak Dhar talked about phase diagram of such a system, and I'm reproducing that here. This is temperature axis, this is pressure axis, this is the region in which solid crystal is stable, this is where liquid, and this is gas. Symmetries are so powerful now to understand this diagram. In fact, Deepak was quizzing you, what is the difference between solid and liquid, if some of you may remember. And here we have a very crisp answer to that. You see, you can go from liquid to gas along this continuous path. And the reason for that is very simple. They both have the same symmetries, rotational and translational symmetries. On the other hand, crystals break translational and rotational symmetries. As a result, to go from liquid or gas to a crystalline phase, you have to pass through what is called as a phase transition. Okay? The fundamental difference between a crystal solid and these phases is their symmetry is much lower. These are rotationally, translationally invariant. These are broken. You will say, well, what is the proof? You just tell us. I'm going to show you experimental proof of this here. Typically, the way you look at atomic structure of a material is by using what is called as X-ray diffraction. You generate X-ray from this tube and pass it through this LED screen, and then this is your object. That object could be your crystal or it could be liquid. And then X-rays get diffracted because atoms are on a lattice, periodic lattice. It acts like a grating. And those X-rays get diffracted and you get this pattern here. If you have a crystal, you get a pattern like this. And if you have a liquid, you get a pattern like this. This is not a real pattern. I have generated it from my computer program, but you can trust it, it's correct. Okay? You see very vivid difference between the two. One is rotationally invariant, one is not. One has definite rotational symmetry of that crystal, maybe 90-degree rotation and so on and so forth. So this is the way I can demonstrate how symmetry, particularly rotational translational symmetry, is broken when you go from liquid to a solid, and that is the most fundamental way to differentiate between the two. So there is something very fascinating about this phenomenon of spontaneous symmetry breaking, and that's where I'm going to talk about Nambu-Goldstone modes, or what is called as rigidity. All of you know rigidity, right? But this is really very fundamental in physics now, and it's associated with this spontaneous symmetry breaking. You see, if I have a lattice, right, like this, crystal lattice, that is stabilized in this region, and I ask a question, Well, it is a broken symmetry state. What broke its symmetry? And then you will say, well, translational symmetry is broken. Translational symmetry means if I translate each atom on this lattice to the right, that's the symmetry I'm talking about. And that is broken unless that translation is basically the lattice vector, as we learned before. But the continuous translation symmetry is broken. So if I translate the entire crystal by the same amount, the distance between atoms don't change. Bonding doesn't change. So energy is not changing. So this has zero energy cost. But if I now displace these atoms in a wave-like manner like this, like this, where you can see it's a translational wave involving transverse sound. Some atoms move this way, some atoms move little less in that direction, pass through a node, and then this way. This is called as transverse sound wave. And it's linked with the same symmetry, except for the fact that I'm modulating it by a sinusoidal wave, nothing else. Right? So this is the wave associated with the broken translational symmetry once you enter the crystalline state. And what you will see, actually this has a finite energy. But that energy goes to zero as the wavelength goes to infinity. Because if the wavelength goes to infinity, I will end up in the same structure as this. And that is called as Nambu-Goldstone modes. In the case of crystal, they are just sound waves. Transverse sound waves, which are not supported in a liquid, because you see when the atoms move along this red arrows shown, it is essentially changing the shape of the unit cell. And in physics, it's called a shear strain, meaning you have a square, you tilt it. That is called a shearing that, using like a scissors. And if you do to liquid, what will happen? If I take liquid block, I apply this kind of force, well, liquid just will flow. And what happens in solid is, well, it goes up and then comes back again. And that's the reason solid can withstand shear wave or sound wave. And that's linked with the rigidity. It has a rigidity built into it against such symmetry operations, because that symmetry is broken. So liquids, no rigidity against shear, and they flow. And transverse sound waves are existing only in a crystal because they have broken that particular symmetry operation. Right? And by the way, this is very fundamental. You can see it in most spontaneously broken symmetries. There are few interesting exceptions which relate to Higgs mechanism, but I won't go into that now. Okay, so rigidity of a crystal, here is a very spectacular demonstration of it. If I take a steel cupboard and I focus on just 4 atoms of this cupboard, right? And I say I'm going to move those 4 atoms by a small amount to the left, the whole cupboard will move. That is rigidity. And that rigidity is a consequence of spontaneously broken continuous translational symmetry, which gives rise to long-range ordering. Each atom is in order. Atom here and atom here respects each other's position due to this rigidity. And that happens due to this broken symmetry state. Okay, so in fact, symmetries are far more interesting. I talked about a general crystal here, in this case, here. Now there are many possible symmetries of crystal, and there are 230 space groups, different kinds of symmetries you can have. So this way you can see now that symmetries can be used to classify crystalline states. There can be only 230 crystals if you ignore magnetism for the moment. Okay, and any material you take, crystalline material, will belong to one of those 230 classes. And those 230 categories are linked with the symmetry groups of those crystals. Okay, good. But there is a remarkable diversity which arises from such broken symmetry states. For example, carbon. Carbon can be in hexagonal graphite state or cubic diamond structure, and they are totally different. Same chemical element can take 2 forms of crystal which are absolutely different from each other. And if you use atomic identity chemistry, it adds to that diversity further. For example, carbon in diamond structure is very different from silicon in diamond structure. Carbon is super hard insulator, whereas silicon is one of the best semiconductors we know today. So symmetry is used to classify crystalline states. I have 2 more topics. Can I go on for a little longer? Please stop me if necessary. This is one example to tell you that science is filled with myriads of possibilities. And you know, by telling you about translational symmetry, crystals, periodicity, you would imagine something like this would never happen. And this is it. If I give you pentagonal tile and ask you a question, can you fill up this space using pentagonal tiles? Can you? No? Because if you start doing that, you find there are gaps. Right? So it says five-fold symmetry is incompatible with periodicity. You cannot fill up the space with just pentagonal tiles. So there was a discovery of quasi-crystals by Daniel Shechtman in '84. He made an alloy of aluminum and manganese and found that if you use that X-ray diffraction I told you, you get very beautiful pattern like crystal. So he was thrilled, wow, this is crystal. But there was a big surprise, because if you see, this crystal has pentagonal symmetry. You see here 1, 2, 3, 4, 5. In fact, if you look at the central peak and count the number of peaks, you will get 10 of them. So you have pentagonal symmetry, and here you tell me that you can't have a crystal with pentagonal symmetry, right? So this was a very interesting event in science. Something discovered something which was totally counterintuitive, but he believed his experiments. And then there was a mathematical theory developed which showed that it is possible to have long-range orientational order without having periodicity, but five-fold symmetry. And here is a Penrose tiling, which is there also on this poster, by the way. Penrose tiling consists of two rhombus, two types of rhombus. One is green and one is little bigger, the blue color one. And with these two tiles, you can fill up the full space such that you have a pentagonal symmetry. You see, you have pentagonal symmetry here. So instead of using one tile, you are allowed to use two tiles of appropriate shape. You can fill up the space and develop long-range order with five-fold symmetry. And this was a really interesting discovery and an example where, you know, new avenues keep opening up in science. And by the way, Shechtman got a Nobel Prize in chemistry for this work. Now, last part of this lecture is about symmetries are not just about fundamental science. They also are going to have direct implications to technological applications that you see every day. Okay? So example I'm going to give you is the broken inversion symmetry, or some people call it parity. So here is an example of an oxide called lead titanate. It's a perovskite oxide. Perovskite is the name of the crystal that it takes. And this is the cubic perovskite structure. Lead atom is on the cubic corners, titanium is atom at the center of oxygen octahedron as shown here. This is at high temperatures. And this is again the example of spontaneous symmetry breaking, but little different. I'll tell you how it is different. And as you cool it down, come to low temperatures, it distorts. This crystal distorts, and this titanium atom suddenly becomes off-centered, okay, along z-axis. And titanium is 4+, oxygens are 2-. What you get is an electric dipole moment, something we learnt in the beginning of this talk. So you develop an electric dipole moment by breaking inversion symmetry or horizontal reflection symmetry in this crystal. What happens then? At the macroscopic scale, here I showed you at atomic scale, but if this happens in every unit cell of my crystal, what you develop is a spontaneous dipole moment, or what is called as polarization, in a slab of this material, which has positive charges accumulated here and negative charges accumulated here. Just like a magnet, but it's an electrical analog. Instead of having north and south poles, you have positive and negative charges here. And if you compress this material by applying external force, you can change this dipole moment and generate electrical signal, because then these charges will change. If you compress it along c-axis, this titanium atom will like to move down or up depending on your force, and that changes this dipole moment, and you can detect it in electrical circuit. Very nice. This effect is called as piezoelectric effect, and it's a consequence of broken inversion symmetry. Okay, you have a dipole moment in the system, it changes by applied mechanical force. That's piezoelectric effect. What do we do with it? Well, lots of things are possible with it. In fact, it's a very big technological application domain. You all have seen ultrasound equipment in hospital. In fact, the first time modern parents see their kids is using this equipment, using ultrasound, and it's based on the same material same kind of material called piezoelectric, where sound wave, if I create vibrations in that material, I will generate electrical signal, and that I can detect and generate an image. Microphone, which I am using here, also uses the same material where the mechanical wave, sound wave, gets converted to electrical waves, and that is how you hear me today. The last example is something you see in kitchen, the lighter, is also made up of similar material, where you have two slabs, and one has up polarization, one has down polarization, and when you compress these two, it basically changes the electrical charges here, and they come out of this electrical wire, generate a spark, and that's what lights your gas. Okay? How is this possible? It's possible because of piezoelectric effect, and piezoelectric effect is possible because of broken inversion symmetry. So breaking of symmetry is very useful as well, not just of fundamental interest. I will summarize what we learned in this talk so far. Symmetries lead to conservation laws, thanks to the beautiful, very powerful theorem by Amy Noether. Symmetries constrain forms of physical laws and even dictate the way two particles or fields can interact with each other. Third, it allows classification of states, not only crystal structure, but elementary particles in high energy physics, and also electronic orbitals for that matter. Symmetries break spontaneously and give continuous symmetries particularly, and give you Nambu-Goldstone modes, which give you rigidity, and that breaking is what gives you diversity in the nature that you see. So much of this diversity we should thank spontaneous symmetry breaking. And of course it has implications to technological important properties. I have a little sort of a conceptual flow picture by David Gross's article in Physics Today. How do we learn about physical laws? Well, you do measurements, learn about initial conditions, and then measure something that comes out of it, and then from that you infer physical laws of nature. What symmetries tell you is, well, the laws themselves have certain couplings and constants and representation, and symmetry principles determine what those laws are, right? So that's the role symmetries have played in these four capacities, and I hope I gave you some elementary introduction how it works, how the system of symmetries works in physics. And here are a few references that I learned, and some of you may find them useful. One is a very nice lecture notes by James Setna. It's a bit advanced, so this is probably for MSc or PhD students. And David Gross's article in Physics Today, Noether theorem. There are some YouTube videos which are very useful and easy to understand. And I also thank Google. I've taken many images downloaded from the internet. I end by saying that the same spontaneous symmetry breaking principle is what governed the cosmological history, starting from the Big Bang, which was the most symmetric object, and as the time proceeded, the temperature started going down, and as temperature cooled down, electrons formed, quarks formed, neutrons, protons formed by essentially the events which are also known as spontaneous symmetry breaking. So what governs these is also what governs the day-to-day life, and it's easy to appreciate and understand. Thank you. There is.
It's not on. Hello? Yeah.
My question is, is in reality, is it possible to have a time, charge and parity reversed universe?
CPT.
Yeah.
CPT. Well, presently CPT. Known universe seems to satisfy those together, CPT. Okay.
But
we don't know whether there are phenomena which may violate that conservation.
Okay. Thank you.
But individually, parity violation is already known. And
Individually, but
that you, yes.
in a large scale,
That's
macroscopic.
right. Sure. But if you ask, I mean, the handedness, almost 99% of the universe still obeys the parity conservation law. Only small part is violated in that.
Thank you.
So you mentioned about the handedness and the chirality, which is the asymmetry. So can you just speak about the helicity and the spin, how it is related?
Yeah, helicity is a slightly different object. It's linked with basically the projection of spin on the linear momentum of an electron, for instance. Whereas chirality is really linked with the symmetry of internal structure of electron.
Okay. So is there any relation between them?
In some cases, they are very closely related. For example, in graphene, you have basically what are called as Dirac fermions, or the electrons. There, the two are more or less indistinguishable, I feel.
So, are there any examples of manufacturing processes that, while manufacturing material, to avoid translational sound waves, you have to, for example, enclose it from interfering sound waves so that there's no point defects during, for example, crystal growth? Or perhaps any manufacturing processes that use sound waves to enforce symmetries?
Okay. I'm not sure I completely understand your question, but I'll try to tell you something I know. I don't know if you have heard of photonic band gap materials. These are materials which are structured on micron scale. Okay, just like crystals, you have electrons, and when you look at electrons in a crystal, you have band gaps, right? And in those band gaps, electrons cannot move those energies. Similarly, in phononic band gap materials, which can be manufactured with certain structure, you can have frequency band in which sound wave cannot pass through them. So you can think of them as defects which are absolutely regularly spaced, or you can just call them as microstructured manufactured material. Yes.
I have two questions. One is related to the temperature, effect of temperature. So why when we apply high temperature, symmetry is always getting broken? Is there any reason for that?
Okay, so it's the other way. At higher temperatures, you typically have higher symmetries.
But when we say, for example, when we heat, crystalline structure or something like that, we say that okay, it is broken and it becomes, or even when we heat something, it becomes more randomized, right?
Yeah. So that's what I tried to explain. Maybe I can go back to that slide. Absolutely good question, and I should clarify that. So this is an example I gave you. At low temperature, you see there is very ordered arrangement of these little electron magnetic moments of atoms. But as you heat it up, they get all randomly oriented. So on the one hand, you will say, this is more disordered to me. And you are absolutely right. This is more disordered, and this is called ordered. That's why this is called ordered phase, disordered phase. But at a macroscopic scale, you are not going to look at atoms now. At a macroscopic scale, this has a magnetic moment which is 0, whereas this has a magnetic moment which is non-zero. So if I apply rotational symmetry along, say, x-axis, this will go to the opposite of itself. So it has a lower symmetry, whereas this one has no magnetic moment. If I apply rotational symmetry, it will go to opposite of itself. At locally, things will look different, but in average sense, they are unchanged. So symmetry of the macroscopic structure is higher in this phase than this one. And it's the entropy which stabilizes that state, typically.
Okay.
Yeah.
The other question is, could you talk a little bit about fractals and the symmetry in the scale?
Okay. Well, again, good question. I omitted it. I don't know enough about fractals to say, but scaling is an operation. So the question is, I talked about rotation, I talked about reflections, translations in time and space. What about scaling? Scaling meaning I have a triangle and I make a bigger triangle out of it. This is called a scaling operation. And unfortunately, most physical laws are not invariant under these scaling laws. In fact, I would recommend you look at Feynman's lecture on YouTube. Again, the title of the lecture is Symmetry of the Physical Law. And essentially, let me ask a question in a really colloquial sense. If I make a bigger and bigger human being, like Frankenstein, will that be more powerful as I increase the size? And the answer is actually no, the bones that you use to scale it up will not be able to support that object. In Feynman's lecture, he gives another example. I make a cathedral out of matchsticks, or you can make a palace out of playing cards. And you ask a question, can I keep making bigger and bigger palace out of it, which is exactly identical to the small scale? And the answer is no, because the mechanical strength will not permit that scaling at all. So most physical laws are not symmetric under those operations, and objects as well, for that matter. But it's an interesting subject by itself, the fractals and self. There are symmetries like golden ratio spiral or logarithmic spiral. They are kind of closer to that idea, I would say.
Yeah, I didn't quite clearly understand why an electric field cannot affect a magnetic field. Can you go across that again?
Sure. Yeah. Okay, so I'm going to assume that my symmetry has either time reversal symmetry or parity symmetry. And then this is my system. You have a magnet bar, Sn, and you apply electric field. Okay, I apply parity operation now, symmetry operation. Under parity, electric field goes to negative of itself, right? And magnet remains the same. Now, my symmetry principle tells me that the physical law which relates the force acting on the magnet by this field should be identical to the force acting here. So that means this force should be this force, but that is actually opposite. This is oppositely oriented with respect to this magnet, the linear force which comes from that. Likewise, if I apply time reversal symmetry, then the electric field remains the same, but the bar magnet is reversed. So you get opposite force here. And opposite force being equal to the force that you get in the original system. Here it's like I'm assuming that there is a force and showing that symmetry tells me that that force has to be equal to minus of itself, and that force hence is 0.
Other questions?
So you told about spontaneous symmetry breaking, and this one. Here, the liquid and gas phase, there's symmetry. So does that mean liquid equals gas?
No. Well, I mean, I agree it's a very interesting question. What it means is you can go from one phase, which is liquid, to gas state in a continuous manner. That's what this means. Excuse me. But the local structure is different. The interatomic distances between gas and liquid are different. So in liquid, you do have what is called a short range order. Short range order means if I look at one atom and I ask how many nearest neighbor atoms does it have, it will be little less than the one you see in crystal, but it will be more or less fixed. Whereas in gases, that's not quite the case. It's much different.
So you mentioned about how conservation laws obey symmetry, and you had mentioned about the gravity part of it. Could you kind of elaborate on that a little, sir?
You mean here?
Yeah, that one. Translation in space with
oh yeah, this translational symmetry. That is in Noether's context. Here.
Yeah,
Yeah. Okay. So the definition of symmetry in this sense is a transformation upon which the total energy of the system is unchanged. Right? So if I bring this object closer to the Earth, you know that its gravitational potential energy is changed.
Yes.
So the total energy will be, total energy is conserved, but the potential energy is changing. Okay. So in that sense, it's not translationally invariant.
Okay.
Other questions? No?
Yeah.
It will be very basic. I just need to explain my son later. That's why I'm asking this question. So you mentioned about a short method of how to determine how many symmetries can be formed out of a cube, right?
Mm-hmm.
So there, is it the similar way that we can apply for any shapes to get how many symmetries can be formed?
Not quite. In the cubic case, I use the fact that you have x, y, z axis which go along the sides of the cube. But if you have, say, icosahedron, then it's not so simple. There you will have to use some other ideas like permutations and so. But the other two Platonic solids that I mentioned in the first slide itself. Yeah. See, these are Platonic solids. This one is a tetrahedron, okay? And you can immediately see that if I have a cube, a tetrahedron can be obtained by taking every alternate corner of a cube. If I connect this, I get exact tetrahedron. So the symmetries of a tetrahedron is a subset of symmetries of a cube. So you can use that for tetrahedron. What about octahedron, which is the next object? This one is also possible. If I again take a cube and take midpoints of center points of each face, I get exactly the octahedron again. You see? That object. And in fact, you can show that symmetries of octahedron are same as the symmetries of the cube. That's why it's called as octahedral group, OH. Yeah.
Other questions?
Does varying pressure play a role in altering objects like graphite to diamond?
Yes, absolutely. Yeah, yeah.
Pressure.
Not only carbon, but there is a whole field of what is called as pressure-induced phase transitions. Okay, so you can break symmetry spontaneously by applying pressure as well. Yeah.
And it's a totally new material.
No, if you start with same chemical atom, you cannot change atoms by applying pressure. Okay, the compound, the composition or chemical formula of that compound will be unchanged. Oh. But the crystal structure can change completely. Oh. Okay, and if you change crystal structure, you can really get very different properties.
Okay.
Yeah.
Thank you.
Symmetry in space, like astronomy. Examples of symmetry in astronomical applications or even theory building. Yeah.
No, so the theories which apply to astronomical observations, they all have these same symmetry principles.
One of the things is that chaos is very regarded, and fields of vision are not always considered to be same at all.
Right.
Is there any application that we can use to project, for example, one could be the transpose of the other, or in some way related to the other, at least theoretically?
Yeah, well, again, a good question. I don't really know definitive answer to it. But the other idea which I told you will apply. In chaos, you often look at trajectories of dynamical trajectories of an object. And if you know the symmetry of the Hamiltonian which governs that dynamics, you can use any symmetry to get a new trajectory from the starting trajectory. So if you know one chaotic trajectory, you can generate another one from it. But I don't know if you can learn something quantitative about things. Maybe there is, but I'm not aware of.
Other questions? So,
Sir, I have one question. Can you throw some light on gauge symmetries?
Sorry?
Like as you gauge symmetries.
Yes. Oh, thank you for asking that question. You know, I didn't talk about gauge symmetries at all in this talk because I really came prepared to give this to high school people with high school science background. But the theories which are used in high energy physics or particle physics, they are called gauge field theories, where you introduce a new type of symmetry operations where the field is locally changed and you study the effect of such symmetry operations. And those are gauge field theories, which I'm not the expert in, but whatever little I know, I will tell you. The easiest way to understand some of this is electromagnetism. You all know vector potential and scalar potential, which give you electric and magnetic fields. So if I add, for example, curl of, you know that curl of vector potential gives you magnetic field. I can always add a function to that curl, let's say gradient of some scalar function, and not change magnetic field. And that is a gauge transformation. You are changing gauge fields, but the physical content in it, like magnetic field, which is a physical field, and electric field, they don't change. That's called gauge transformation. And since the physical things don't change, it's also a symmetry operation. But those are really fundamental. In fact, much of the modern theories in particle physics, standard model, as well as string theory, are based on gauge symmetries. So I should definitely, it's a very important aspect here.
Other questions?
Okay, so since the discussion went a bit deep, so can you just give some idea about the cosmological symmetry breaking, Nambu-Goldstone boson and other things?
Sorry?
The cosmological symmetry breaking in the early universe. Can you give some simple ideas about that?
Well, the only thing I know is the Big Bang had all the possible symmetries. And as time proceeded, the temperature of the Big Bang came down, and that led to spontaneous symmetry breaking, as I showed in that cosmological history, along the same mechanisms that I showed. Okay. The Goldstone modes are called massless excitations, whereas there are also spontaneously broken symmetries where you have mass excitations having mass, and those are called Higgs bosons. Okay, and that's also linked with materials to superconductivity, but that's the way things happen, roughly speaking. But I really am not expert, and I shouldn't say much more than that.
Thank you.
Any other? Oh, there's one more.
Sir, how is entropy related to symmetry?
Entropy?
Entropy, increase in entropy.
Yeah.
Related to symmetry.
Okay. Well, yeah. So entropy, in some sense, is a measure of disorder. But if there is no breaking of symmetry, spontaneous breaking of symmetry, entropy contribution to free energy will still have the same symmetry properties as the total energy that I talked about. Okay, but when there is a breaking of symmetry, like phase transition I talked about from paramagnet to ferromagnet, there the entropy does play a very important role in condensed matter systems.
Only in certain systems does it play a role, or is it?
No, in most materials that I talked about, it's the entropy which plays an important role of changing at the breaking of symmetry.
Other questions? No? Okay, so I guess before we break up, I wanted to point out the angular momentum conservation part that he pointed to. There is a nice, what do you call, merry-go-round, something like that, in the park just outside. So before you go, maybe you want to go and take a relook at that one if you hadn't seen it before, and think about symmetry while you are trying to fall or not fall. So, okay, I think with that then let's thank Umesh for a wonderful talk. And
thank you.